Hello, my name is Robert C. Gray, and I'm a PhD candidate in digital media at Drexel University. On behalf of co-authors Jichen Zhu and Santiago Antonyan, I will be presenting our research on regression oracles and exploration strategies for short-horizon multi-arm bandits for the 2020 IEEE Conference on Games. We do look forward to feedback on this ongoing work, so please feel free to reach out with any questions or comments. My info is both in the paper and at the end of this presentation, and I look forward to hearing from you. And with that said, let's talk a bit about short-horizon multi-arm bandits, also called MABs or just bandits. MABs are a class of sequential decision problem, where an agent must make a series of choices among a potential set of actions, where each choice will offer a reward that is not known until it is made. This agent wishes to maximize the total reward that they receive from their string of choices, and so it must somehow split its efforts between exploring the options, to see what reward they offer, and exploiting the option it believes to be the best. And a lot of research has gone into exploring the policies that such an agent might use to make those choices. Our particular domain is that of player modeling, where we can use observations of a player's behavior in a game to estimate qualities of that player. Depending on our goals, we can then use these estimates to determine the player's designation within a model that allows us to predict gameplay preferences, anticipate player behavior, and so on. Specifically, our work has been motivated by the domain of lifestyle exergames, where we hope to learn features of an individual player that will assist a software intervention designed to increase the number of steps walked by that player in their daily life. We've found in previous research that classifying a player modeling problem as an MAB problem can serve as an effective method for implementing a player model that is based on observed behavior. However, when deploying these techniques in a domain like this, we encounter an under-researched area of MAB strategies, specifically short-horizon MABs. The horizon of an MAB refers to the number of choices the bandit strategy is requested to make, and therefore the number of observations it is permitted to observe in its sequential decision task. Typically, MAB strategies are studied in the limit, where this horizon is extremely, or in some theoretical analyses, infinitely long. But when attempting to model a player after only a handful of behavioral observations, we deal with a considerable amount of noise in the data for a given individual. Modifying bandit strategies to function more effectively in short horizon contexts is the focus of our research. Toward this, we investigate three different ideas. The first is in integrating regression models into the oracle of the bandit strategy to help identify higher yield opportunities faster when working with non-independent observational data. Second, we explore the potential benefits of forced exploration periods that engage purely in exploration initially before engaging the bandit strategy. Third, we compare several popular MAB strategies to one another when operating in a short horizon, including a new variant of the upper confidence bound or UCB strategy we call UCBT that can automatically adjust its exploration constant. Our empirical results show that all three ideas can help significantly in the short horizon scenario. Although our best performing strategies were variants of Epsilon family strategies incorporating ideas from 1 and 2, we did find that UCBT compares favorably to UCB1 when the exploration constant is not properly tuned. To more effectively describe our solutions, let us formalize our definition for an MAB problem. The most common instantiation of the MAB problem is the Stochastic Bandit problem, where the rewards for each arm result from a static underlying distribution of potential reward values that are known only to the arm itself. So even when the agent retrieves a value from an arm, it cannot be certain how accurately that single value represents the true expected value or variance in reward that the arm provides. Since the goal is to maximize total reward over the full horizon, MAB strategies implement policies that aim to strike a balance between spending decision opportunities to learn more about these distributions, exploration, or maximizing rewards by capitalizing on the knowledge already gained, exploitation. This policy is informed by an oracle, the term we use to refer to the mechanisms inside the MAB that predicts the expected reward we will obtain if we choose a given arm. When the policy determines that it is time to exploit and choose the arm with the greatest expected reward, it is the oracle that makes this prediction. And depending on the particulars of your MAB problem, we believe the choice of oracle can have as much impact on MAB strategy effectiveness as the policy itself. Other MAB variants have experimented with alternative oracles, and even regression-based oracles, such as contextual bandit problems, where the reward distributions are influenced or at least correlate with some external vector. Our domain of modeling players in multiplayer exergames does not classify as a strict stochastic bandit problem, and therefore we find relevance in additional MAB problem variations such as non-stationary bandits, where the reward distributions cannot be assumed static, and restless bandits, where some arms may become intermittently unavailable. Regarding short horizon bandits, a recent approach by Tompkins and others attempts to select policies for individuals within a group by exploiting knowledge of rewards from arm pools with other users, adjusted by a factor of similarity among users. Though this is a promising approach under certain parameters, we seek out what can be done in more general situations where access to data from other users is not assumed. In exploring these ideas, we leverage simulation to evaluate different strategy variations. Therefore, we should take a moment to discuss our motivating scenario and the design of these simulators. As mentioned, we formulated the problem of modeling players of a multiplayer Exergame as an MAB problem. Imagine that we are presenting players of a daily Exergame with a motivational stimulus in their daily session with the hope that it will result in increased steps for that day, as measured by a Fitbit. Previous research has demonstrated that presenting the right variant to the right player can have a significant effect on results. We want to construct an agent in the form of a bandit strategy that could achieve this automatically. So this bandit strategy chooses among 3 arms, let's call them arms A, B, and C, that will change the experience of the player's daily Exergame session. So the bandit chooses arm C for that player, and then observes the daily steps recorded by their Fitbit that day following the game session. Those steps are interpreted by the bandit as the reward for choosing that arm for that player, which will guide the bandit's decisions for that player in the future. Such an experiment is not part of this study, though we will present the results of such a study at FDG next month, but here it is offered as an example in which this approach, and the techniques we will discuss, can be useful. It would be reasonable for a study like this to only last a few weeks, and for an MAB strategy to be effective, it would need to learn the player's preference and converge on the arm with the highest reward for that player within a very short time. We set up a simulation with a virtual player that generates daily step data in response to a motivational stimulus. For each time period, the bandit strategy will pull one of 3 arms and attempt to maximize the reward, the daily steps, over the course of the study's horizon. To generate realistic daily step rewards from these virtual players, we use data from a mechanical Turk experiment conducted in 2016 by Furberg and others that collected participants' daily steps measured by a Fitbit. We graph a histogram of those daily steps to get a sense of the distribution, and based on literature regarding human walking patterns and other voluntary intermittent behaviors, we fit a gamma distribution. Here you can see we overlay the probability density function for this distribution in blue. Our first simulator, which we named the Stationary Step Simulator, generates daily steps for a virtual player by randomly sampling from this distribution. However, we also know that the nature of human walking behavior is not fully replicated in this approach. For instance, we would anticipate that a person's steps on a given day are somewhat related to their steps the previous day, or the same day in the previous week, at least more so than a random value. Therefore, in our second simulator, which we call the Pattern Step Simulator, we constructed a regression model from the sequential step data using the 7 days prior to a given step count as the features of the regression. We then used backward elimination to construct a minimal model, iteratively removing features until all those remaining had a significance of p less than 0.05, and all features survived this with p less than 0.001 except for the steps 5 days prior. We take the coefficients for these features resulting from the regression analysis, and we use it to reconstruct what a virtual player's steps should be on a given day, given the steps it reported the 7 days prior. We combine that with a random pull from a gamma distribution to blend the 2 approaches. In doing so, we are able to generate a sequence of steps that not only conforms to the distribution of our mechanical Turk dataset, but also maintains the expected relative correlations among days. To show this, we have in this figure the same histogram of the human step data overlaid with a frequency histogram in blue of 500,000 steps generated by our pattern step simulator. As a sanity check, we also run a multiple regression on those 500,000 steps we generated, exactly as we did the human behavior data. As expected, we found the resulting coefficients shown in this table, where the S sub t-5 component was again removed in the backward elimination. As you can see, we were able to achieve a very close approximation in our simulator to what was observed in the real human step data. Since we're using a bandit strategy to administer an intervention, what remains in our step generation is a way for our bandit strategy's selection to have some influence on that virtual player's steps. And for our formulation, we define 3 arms, A, B, and C, with different levels of effectiveness, that each correspond to an oracle value and a relative adjustment range. When an arm is selected, the virtual player's generated steps are increased by a factor uniformly sampled from this adjustment range interval. For example, if the step generator for a virtual player rendered 6,500 steps, and the Bandit strategy selected arm A, a demotivating arm for that player, a random value is selected from the interval -0.2 to 0. Let's say it's -0.05. This is then used to render the final step reward of 6175. Now let us discuss our 3 ideas for improving MAB performance in short horizon scenarios. The calculation procedure that is used to predict an arm's reward value before it is pulled is what we call the oracle of a Bandit strategy. Typical oracles predict arm values using descriptive statistics of past rewards. For example, one might determine the expected value of a given arm using the average of the rewards observed from that arm in the past. Our proposed method replaces the standard oracle used in these strategies with a regression oracle that makes a prediction not just based on the rewards observed for a given arm, but the rewards observed for all arms. Instead of keeping separated records for each arm, we construct a linear regression model in which the arm is provided as a feature. Depending on the specific domain, we can also include other predictive features, as one might do in a contextual bandit. Or in our case, because we know human daily step data to be patterned, we can feed past step data back in to exploit those patterns and hopefully achieve more accurate predictions at baseline. Each time an arm is pulled, we add to our record this input vector as independent variables, and the player's resulting steps as the dependent variable. We then perform an OLS regression on all such records, resulting in a set of regression coefficients, beta. When it comes time to make a choice, our oracle predicts the results of each arm by constructing a hypothetical input vector for each arm and estimating its reward based off the current regression coefficients. Since each hypothetical input vector is associated with an arm, the one that estimates the greatest number of steps is presumed to indicate the best arm to pull. Again, it is worth mentioning that this formulation is reminiscent of a contextual bandit, but we note that even when the problem does not involve an external vector, this approach may be more effective than standard approaches when dealing with data that contain underlying patterns. Further, we propose that this strategy should at least do no worse than a traditional strategy when no pattern is present, though that is a topic of our future work. Many bandit strategies, like Epsilon-Greedy, rely on stochastic exploration of the arms. However, in the short horizon setting, we may not have the luxury of stochastic exploration, and may instead need to jumpstart the bandit strategy with heavier exploration up front. We address this with what we call a forced exploration period, in which each arm is pulled an equal number of times in random order before the bandit strategy is engaged. To examine this potential, we compared a range of MAB strategies in both simulators. Epsilon-Greedy selects the best performing arm so far, except when it chooses to randomly explore, with a probability designated by epsilon. Epsilon-Decreasing is similar to Epsilon-Greedy, except with a decaying exploration threshold. UCB1 selects the arm with the highest potential based on an estimate of the confidence interval around the average of past rewards. UCBT also selects based on a confidence interval, but it constructs the CI explicitly via student's t-distribution. UCBT is computationally more expensive, more so as the horizon grows very large. However, in the short horizon scenario, this is not a concern, and there are cases in which this approach can provide advantage, as we will demonstrate. Finally, we include variants of both Epsilon-Greedy and Epsilon-Decreasing that replace the traditional average-based oracle with the regression oracle previously discussed. This leaves us with 6 bandit strategies, each of which would be tested on both the stationary step and pattern step simulators, and each of which would be evaluated with and without a forced exploration period. We also run an experiment to evaluate UCB1 versus UCBT. Our experiments were conducted with a horizon of 70, in other words 10 weeks of assuming daily interaction with a player, which is significantly shorter than what is usually considered in bandit literature. We ran each bandit strategy in each context 1 million times, and averaged the reward at each of the 70 time steps to observe relative performance among the strategies. For the strategies that involved a tuning parameter, such as epsilon or the C parameter in UCB1, these went through a pre-evaluation in which the bandits were run with arrays of potential values for that parameter to find the value at which the bandit performed best. This was done separately for both simulators. We first examined the performance of the 6 strategies in the stationary step simulator. Here we see the 2 regression oracles, blue and purple, outperform those with traditional oracles. In these traditional variants, the expected reward of each arm is calculated independently from each other, However, in the Regression Oracle variants, rewards observed from all previous iterations, including those observed for other arms, are factored into every prediction. Looking at the pattern step simulator, where the Regression Oracle is able to take advantage of the underlying patterns in the data, we see again that the regression variants outperform the traditional oracles in the short horizon. They are able to pull ahead as early as pull number 10, indicating that the Regression Oracle requires very little data to begin making a difference. The previous two experiments were repeated with forced exploration periods of 4 pulls per arm. Here the results of the forced exploration runs are shown underneath their non-forced versions. The use of forced exploration means lower rewards during the forced steps with the expectation of higher rewards afterward that will help reclaim that cost. Looking at the last 7 days column in the results tables, we can compare forced versus non-forced for any strategy to see that forced exploration generally achieves higher rewards in the final pulls. However, if the horizon is short, the average reward across the horizon may still end up lower. We conclude that, depending on the specifics of the application domain, sufficiently short horizons, even shorter than our 70, might not see advantage from forced exploration, where ours and longer ones might. It can also be seen in each of these experiments that UCBT, shown in yellow, does not generally outperform UCB1 in orange, where it appears that matching UCB1 is about the best it can hope for. This is in line with our intuition, where UCBT is fundamentally the same approach as UCB1, only with a different calculation for its oracle based on confidence intervals. Earlier we mentioned that several of the Bandit strategies had to undergo pre-evaluation. In the case of UCB1, this involves finding the optimal value for a parameter C that adjusts the confidence interval calculations to match the domain reward's order of magnitude. However, tuning this parameter is not always possible or practical, especially in real-world examples. Some rewards may be unbounded, each individual player might require a different tuning, or the strategy may only get one opportunity to run and can't afford a pre-evaluation. If this C parameter is poorly tuned, it can harm UCB1's performance. This experiment shows a run against the stationary step simulator with a properly tuned UCB1 in orange, a poorly tuned UCB1 in green, and the UCBT strategy, which requires no tuning, in blue. Here we can see that although there is a slower start for the UCBT strategy, it quickly catches up to the optimal UCB1 in a relatively short horizon. Most important, it very quickly outperforms the poorly tuned UCB1. One of the main contributions of this paper is the idea of using a regression oracle in multi-arm bandit strategies. Rather than calculating the expectation over all the previous pulls of an arm to estimate its reward, we suggest the use of a regression model, linear or otherwise, that can take into account all data obtained for the problem to date. In real-world bandits, where each arm might represent a potential intervention with real human subjects, the reward among arms is likely correlated. The player we are selecting for likely has general characteristics that will influence the reward independent of the arm that we select. Therefore, we believe it to be more appropriate to use this regression model to understand the system as a whole, not just as isolated arms. We acknowledge that with the introduction of the regression oracle, we may not be adhering to a strict bandit formulation since we are no longer stateless. But just as real-world applications can break the assumption of arm independence, as we just discussed, the assumption of statelessness may also be broken when a bandit acts repeatedly with the same human subject, especially when administering an intervention. However, we still find it effective to address these problems via bandit strategies. It is also worth noting that in the long horizon, we do not expect to see any benefits from a regression oracle, where the oracles for other bandit strategies discussed in this paper will all converge to true values in the limit. We emphasize again that our work is in improving bandit performance in short horizon scenarios, which have been understudied in the literature but are applicable in many real-world problems. Our results show that regression oracles applied to standard Epsilon-Greedy and Epsilon-Decreasing strategies were found to be the best among those we experimented with in the short horizon setting. Further, we found that forced exploration periods have the potential to increase average short horizon performance based on the specifics of the domain. Finally, though more theoretical analysis is warranted for the UCBT strategy, it does appear to hold potential for situations in which UCB1's C parameter is impractical or impossible to tune ahead of time. Once again, I am Robert C. Gray, speaking on behalf of co-authors Jichen Zhu and Santiago Antonyan. Thank you very much for your interest in our research and for your time today. We are also grateful to the National Science Foundation for helping to fund this work. Please feel free to reach out with any questions or comments, and I look forward to hearing from you.